Consider the following situation. We have a triangle and its circumcircle, and we take the angle bisector of one of its angles, and we intersect it here with the circumcircle. I'm going to prove that this point here always lies on the perpendicular bisector of this side of the triangle, or in other words, that this length equals this length. Well, proving this is not really hard, because we have this cyclic quadrilateral here, and so this angle equals this angle, and this angle equals this angle. Now, if this is the center of the circle, and this is our point that lies on the perpendicular bisector of this line, we know that the center lies on the perpendicular bisector of this line because this equals this as a radius. And so this is actually perpendicular to this line. Well, since both points lie on the perpendicular bisector, then the line defined by these 2 points must be the perpendicular bisector. And so it's perpendicular to the base of the triangle, and it intersects it at the midpoint. Well, suppose now that we didn't know that there was a circle, but instead we just took the angle bisector here and intersected it with the perpendicular bisector at some point. How do we prove that this quadrilateral is cyclic? Well, we basically already proved it, because there is a unique intersection of the angle bisector with the perpendicular bisector, and we already saw that if we take the intersection of the angle bisector with the circumcircle, then this intersection point is that unique point. And so there's no other point that could be the intersection of these 2 lines, but the one that is the midpoint of this arc, or that lies on the circumcircle of the triangle. Now I'm going to give you an example of how a person might approach this problem in the wrong way, so you can see what you shouldn't do if you're trying to solve this problem. For example, one might tell you that this triangle here and this triangle here, that they're congruent because they have an equal angle here, they share this side, and also this side equals this side. And so they must be congruent because they have 3 equal elements. Let's see what happens if we assume they're congruent. What happens is that this side must equal this side, which is plainly wrong. We didn't choose the initial triangle to be isosceles. And in the video about congruent triangles, I explained that there are some situations in which it might seem that the triangles are congruent, but they actually aren't. And this is exactly the same case when we have 2 equal sides and 1 equal angle. But that equal angle either has to be between those sides, for example here, if we had that this angle equals this angle, or it must point towards the larger side of the 2 that are given. So if it was here instead, if we had this angle equals this angle, then it would point towards this side, which is obviously the larger one. This side is larger than this side. And in these cases, it would have been true that the 2 triangles are congruent. But in this case, it's not true. We can make it true, however, by constructing this segment like this, so that this equals this equals this. And in this case, this triangle here would be indeed congruent to this one. So essentially what we did is we took the symmetric point of this one with respect to this line. So we did symmetry with respect to this line. This point goes here, and now we know that these 2 triangles are congruent. So if this angle here is phi, then this angle here must be phi. But then this angle here is 180 minus phi. And therefore this angle here, because of the isosceles triangle, must also be 180 minus phi. And so we get that the sum of this angle and this angle is 180 degrees. And therefore this quadrilateral is cyclic. And that's what we needed to prove in the first place, that this point lies on the circumcircle of the triangle. So in conclusion, if we have a triangle and we have an angle bisector intersecting a perpendicular bisector of the opposing side, like this, then this point here, the intersection point, must lie on the circumcircle of the triangle, and it's the midpoint of this arc here. And now we're going to look at the analogous statement, but for the external bisector instead of the internal bisector. So external bisector we get by extending this side and taking the angle bisector of this external angle of the triangle. We intersect it with the circumcircle. Now instead of getting the midpoint of this arc here, we get the midpoint of the complementary arc, the other one, the larger one, here. And here's how we prove it. Well, this quadrilateral here is cyclic, and so this angle equals this angle. On the other hand, we also know that this angle here plus this angle here is 180 degrees. And so this angle here, which is 180 minus this one, must equal that one. And therefore, this triangle here is isosceles. This side equals this side. And so again, if this is the center of the circle, this line would be the perpendicular bisector of this side. Now we can connect the midpoint of the small arc with the vertex and mark the other angle bisector here. And now we know that there is a right angle right here. This here is a right angle. And we've already studied this, but now we can confirm it because the perpendicular bisector here passes through the center of the circle. And therefore this is a diameter. And when we have a diameter of a circle, then the angle that it makes with any point on the circle is 90 degrees. Now let's recap again. We have a triangle, and we take the perpendicular bisector of this side. Then if we take the angle bisector and intersect it here, if we take the external angle bisector, then not only this angle is 90 degrees, but this point is the midpoint of this arc of the circumcircle of the triangle, and this point is the midpoint of this arc of the circumcircle. And so these 5 points lie on the same circle, like that. Here you see the optional problem. We have a triangle, and this is an angle bisector, and this is an angle bisector. And then we took the perpendicular bisector of this segment here, the angle bisector segment, and this perpendicular bisector intersects this angle bisector at this point. And then we take this line here, and we construct a parallel line through this point, like that, and then we intersect it here with the angle bisector. And that's how we also get this segment. We have to prove that this blue segment equals this blue segment. These two lengths we need to prove are equal. And here's the solution. Consider first what we need to prove, and consider this quadrilateral here. We have an angle bisector, and we need to prove that this equals this. So we need to prove that this point lies on the perpendicular bisector of this side. So if you consider this triangle, it has an angle bisector, and we need to prove an intersection point between a perpendicular bisector and an angle bisector. So this point should be the midpoint of the arc, this arc, of the circumcircle of this triangle here. So these 4 points must lie on this circle. So we need to prove essentially that this quadrilateral is cyclic. Suppose that we prove that it's cyclic, then this angle would be equal to this angle, and this angle would be equal to this angle. And because these two are equal, then these two here would be equal, and so this would be an isosceles triangle as needed. So essentially we need to prove that this angle here equals this angle here. But we know that this angle equals this angle. And so the only thing we need to prove is that this point, this point, this point, and this point lie on the same circle. Because then this quadrilateral here would be cyclic, and we would say, oh, this angle equals this angle. But wait, you see in this triangle here, we have an angle bisector and a perpendicular bisector of the opposing side, and they intersect at a point. And we know that this point lies on the circumcircle of the triangle, and is the midpoint of this arc. And so this angle equals this angle, which equals this angle, as needed. And therefore, this quadrilateral is cyclic, and therefore, this equals this.